Cool. Um, Somebody emailed me over the weekend asking me for advice about what we can do to like study and prepare for the final exam. Um, I've got about half of it written so far, so don't take my word that it won't change or whatever. I don't really know all the things, but everything throughout the semester is fair game. But we've been building up our skills a lot. Like the first one was much more about individual molecules and things like that, and like learning how to keep track of molarity. You should be good and skilled at doing that, and that should stay throughout this. Um, you can reasonably expect 4 questions, I think, on this. One of them should be something similar to what we're doing right now with Gibbs or like entropy or enthalpy. Any of these things should be fair game. There should be something that's ideal gas. There should be something that's a Lewis dot structure, and there should be something that's calorimetry. Those are like the 4 things that we've done since our last one. Those seem like they're 4 easy, safe bets. We will have a big review session on Monday next week. So that'll be a good chance for you to bring in your current cheat sheets in whatever format they're in and help tweak them along the way. Because, yeah, but it'll be a big fun review session. Any other questions? Cool. Um, all right. Then let's get on with Gibbs free energy. So what we've been talking about lately is entropy and enthalpy and just like heat exchange and how these things all come together. And so we've got a couple different like reactions based on their entropy and how spontaneous they might actually be happening. The baseline for this is just like if something is melting, usually we're going to have our delta S, it's going to be greater than 0 um, for that, and it should be spontaneous. If we are if our T is greater than the melting point. Sorry, I needed an extra column in this and I wrote a wrong thing. So if our temperature is greater than the melting point, we should have an S that is going to be greater than 0, and our reaction should occur. So I'll give that a plus. If we're at the melting point, we're going to be in equilibrium. And if we're less than that, then we're going to get something that is non-spontaneous. Yeah.
What is like spontaneous equilibrium? Spontaneous.
Is this reaction going to happen? So if I heated something up where it got over, like if I had just some ice and I heated it up over 0 degrees Celsius, it is going to become liquid water at that point. That is a reaction that is going to happen no matter what. Um, it is a reversible reaction where we can make it go back to ice again, but it's not like you're going, unless you have really weird pressure and other situations, you're not going to have ice that is above the melting point. That just it will go through a phase change.
Yeah.
So that's all. Does that answer your question?
So equilibrium, the non-spontaneous.
So if we were at 0 degree perfectly, then we could have a slight mixture of ice and water. So some of it will have enough energy to actually melt a little bit, and some of it won't be. But there'll be, if we were to actually hold this at perfect 0, there is an equilibrium um, between those two. Does that make sense?
Yeah.
Okay. And then once we get to below 0 degree, then we're back to ice and it just stays at ice and it's a non-spontaneous reaction. ice that is frozen and stuck in your freezer is not going to spontaneously become water unless it undergoes a lot of heat or possibly a lot of pressure. Like if you go ice skating, your ice blades are usually putting so much pressure on the ice that you form a really small layer of water underneath you every time. It pretty much freezes up immediately afterwards, but your amount of pressure is causing that ice to instantaneously melt. So, okay. So similarly, if we were to have something that is possibly instead of melting, we're going to have our freezing point. We're going the other way. We're going to just do this pretty quickly. We are now going to try and go the opposite direction where we're trying to freeze things. We're just going to see everything kind of stay in the same, but also reverse it a little bit. Yeah, we're pretty much rewriting the same thing. We're just going in the opposite direction where if we are greater than the melting point in this situation, we're going to be considering it from the other side of this where we are trying to make ice. So our delta S will be less than 0 and it'll be a non-spontaneous reaction. But if we get under the melting point, then we get to make ice and it'll be a spontaneous reaction, hopefully. So the reason why we're talking about just basic melting and freezing is because in the early 1900s, we have William Gibbs, who started noticing some of these trends and wanted to better classify when reactions are going to actually happen and how much heat and energy is going to be necessary to make them happen. So he developed the idea of Gibbs free energy. And this is going to just be the relationship between our heat, enthalpy, and entropy. So he wanted to have a better way to understand how all these different types of energy are interacting together, whether or not something is going to be spontaneous or not, if that reaction is actually going to proceed and move forward, and how much energy does it actually take and require to get to it together. So our definition for this, or at least the baseline version, is going to be our delta G is equal to our delta H minus T delta S. Where Gibbs free energy is going to be impacted by both our enthalpy as well as entropy based on whatever temperature we're at. And that temperature is going to change whether or not we are possibly freezing or we are possibly melting something. Maybe we have an exothermic reaction or an endothermic reaction. Any of these things can possibly change. But essentially, if we have a negative delta G, we are going to end up having a reaction that should be spontaneous. And that's kind of like the big takeaway for us. So we're going to still assume our constant G and constant P for this. So if we have, nope, wrong color. a delta G that is going to be less than 0, and we'll put a delta G that is greater than 0. What does this mean for us? We have a spontaneous reaction. And here we'd have a non-spontaneous. Our spontaneous reactions are going to be product favored, where we want to make whatever is going to be on the other side of this, whereas the non-spontaneous ones tend to be reactant favored. And then the way that we always write these is going to be based on what we're trying to make. So we like to write these as a forward reaction versus a reverse reaction favored. And there's a lot of context that we need to just understand what is going to be forward versus backwards. But we need to think about like what product do we want to make? So we might have something like our reactant and our product. All I'm going to do is just have our H2O as a liquid, and it can turn into H2O as a gas, as a product. So if we were to increase the temperature of this, then that is going to become a spontaneous reaction. And hopefully we are going to see a forward reaction where we're moving from H2O or from a liquid to a gas. And then if we were to cool the temperature down again, then we would get the reverse reaction favored, where we're starting off with this and it's going to become back into equilibrium from a gas to a liquid. So when we talk about forward versus reverse, we just need to declare what we think our product is going to be. And that can be vary based on any number of like chemical reactions that you're doing. If it's us breathing in, where we are just taking in oxygen and some carbon substrate, and we're going to exhale CO2, my product is probably going to be the CO2. And that is something that is only going to be really moving forward. I don't take in CO2 and make it go in reverse the other way. Does that feel comfortable-ish? Cool. The actual like solving of these kinds of equations are really similar to what we've been doing. It's not going to be anything super new. Sometimes we're going to use this equation up here. That's going to be when we're actually given the heat and enthalpy of our reaction, and we can solve for some of the entropy parts. But we can also look at all the individual contaminants or reactants on their own, as well as the products. So we can have another form of this equation, which is going to be delta G naught of our reaction is equal to the sum n delta G naught F products minus the delta G we're just going to leave that F out. We don't need those. Reactants. And we're going to assume this at 1 atmosphere and also our standard room temperature of about 298 Kelvin. But this equation down here, this is again just what we've been doing for a while with our like entropy, where we're just taking all of these terms that are in the back of our books. Like we're going to look at that appendix, we're going to find those values, and we are going to calculate a total value from this. So we're going to try to work through one or two problems together as a class. so we can figure out just how to actually apply this. So we've got diatomic nitrogen and oxygen molecules make up about 99% of all the molecules in a reasonably unpolluted dry air. We want to evaluate the delta G for the following reaction where we're going to turn it into nitric oxide or nitrogen oxide. So we want to know, is this reaction spontaneous possibly? And we also want to be able to calculate our delta G for this. So a couple things that we want to do is we're going to, one, look up our delta G naught values in Appendix K. You don't have your textbooks out with you right now, so I'm just going to give you these values. So our nitrogen gas, specifically as a gas, is actually 0. Oxygen gas, also 0. These are freely just available and around the atmosphere. But then we've got our nitric oxide. Nope, it's just NO, not nitrous oxide. And that is 86.57 kilojoules per mole. I will say you do have one more homework assignment. It is just 2 problems, but it is solving something exactly like this because I just want you to have a little bit of familiarity going to the back of the textbook. For the final midterm, you will have all the values written out in the test very explicitly for you. You will not have to bring an appendix. You will not have to go searching for this. They will all be right there in front of you. Cool. So I want to know if we are going to make nitrogen oxide spontaneously in our atmosphere, just because we've got all these things floating around. So we're going to do our big equation. Where we've got our delta G of the reaction is going to be the sum of N delta G products minus sum of N delta G reactants. So how many moles of our product am I expected to have? 2 moles, great. So we've got our 2 times, we've got our delta G of our products. We've got that 86.57 kilojoules per mole. Together, those make up and comprise our nitric oxide. Great. And then for all of our reactants, those are both 0. So we could technically have 1 times 0 plus 1 times 0 if we really want to be very redundant. And we'll pretend that that one is for nitrogen gas and that one's for oxygen, just so we can keep track of everything. And all that should equal our delta G. What's up? Okay. So our delta G of our reaction is just going to be 2 times that 86.57, which should equal 173.1 kilojoules per mole. And our last step is to interpret this. Is this a spontaneous reaction based on having a positive delta G? Scroll up. No, non-spontaneous. So we are not filled with a bunch of nitrogen oxide in the atmosphere all over the place just because these 2 molecules, like oxygen and nitrogen, they are all around us, but they are not spontaneously happening. So this is a non-spontaneous reaction. if we were to possibly change our temperature or like some of the pressure and other conditions, maybe we'll have to reevaluate this. But just using our basic pressure and our common temperature, no. Did we answer your questions? No, no, just like fix it. Cool. So that's using this second equation down here. I would like to try one problem where we have to use the first equation up above. So we have make the same determination. Did I? Okay. So we're going to be using this based off of our first equation, where we're going to see using the heats of formation and absolute entropies rather than the free energies of formation. So we're going to do the same exact reaction that we have up here. We're going to try and solve it the opposite way and see if we can get the same results overall. So for this, we're going to need to use our appendix to calculate our entropy as well as our enthalpy and our entropy. My gosh, words. So we're going to do the same kind of thing. We're going to obtain values. So I've got our nitrogen, our oxygen, and we've got our nitric oxide. These are going to have values for our delta H of formation, where that's going to be 0, 0, and 90.25. And then we've got our delta S naught. And somebody went out and spent a lot of time trying to figure out all these calculations for all of these things. All of these values should be in, oh, there is actually a little bit of a difference. This one is kilojoules per mole. And then we've got one other slightly different unit for our S naught that is in joules per mole Kelvin. So we've got all of these values. Now we got to actually figure out how to work with them. Let me do a thing really quick because I need more space than I gave myself. Come on, why won't you let me do this? All right, we're just gonna move things down. Why won't you let me do this? All right, screw it. It's fine. Cool. So now we need to go back and try and calculate all of our different components for this. So we need to calculate our delta H, and we are also going to our delta S. So for our delta H, we're going to now do our baseline reaction for this, where we've got delta H of our reaction is going to be equal to the sum n delta H products minus the sum n delta H reactants and similarly, we've got sum of our entropy minus the sum n delta S products. So we're gonna have to do these two calculations. I would love to just like, Ava and Lucy, you are gonna be the split on the class. So if y'all can take care of our delta H, I'm gonna have y'all take care and try and solve our delta S. Cool? Sorry. Who's got some answers for me? What do we got? 24.9. Yeah. 24.9 joules per mole Kelvin. Great. What's our delta H? 180.5. Cool. I wrote out all the like little steps here so that you could possibly go back and follow it along. So now that we've got these two values, we need to actually calculate our delta G. And we'll do our first reaction, which is delta G of our reaction is equal to delta H minus T delta S of our reaction. So this is going to be our 180.5 kilojoules per mole minus our temperature is going to be 298 Kelvin times, I'm going to write this a little bit differently just because I want our units to actually match up. So I'm going to take our delta S and I'm going to convert it into kilojoules as well. So it's going to be 0.0249 kilojoules per mole Kelvin. And I'll put a little note here. That we are just converting that to kilojoules per mole. So we can make our math a little bit easier and our units can line up properly. Oh my gosh, get this out. Cool. Cool, so we've got 298 times 0.0249. I totally wrote the wrong thing in my calculator. 0.249 So that should be 7.42 kilojoules per mole. And it's only kilojoules per mole because we get to cross out. Oh my gosh, stop doing this. Sorry, it's being very rude today. Our Kelvin and our Kelvin get to cross out. 5 kilojoules per mole. And then our final answer should be delta G of our reaction. Going to be 173.1 kilojoules per mole. And then again, because we've got a positive delta G, this is non-spontaneous. But we were essentially able to prove the same thing using this same equation twice in different ways. One where we've already calculated all the individual delta G's and they are all available in your appendix. But if they weren't available in your appendix, we can go through this much longer, a little bit more rigorous way. And this is how we're going to be able to connect our enthalpy and our entropy together. So we've got 173.1 kilojoules per mole for this answer. And if we scroll up here, we got the same 173.1 kilojoules per mole. We solve the same thing in just two slightly different ways. What's up?
What's G actually?
Delta G, that is our Gibbs free energy. It's just the relationship between enthalpy and entropy. It is literally just a way for us to figure out how do all these little pieces combine together and make our life a little bit more simplified. Instead of trying to know like plus or minus for H and S, whether or not a reaction is going to happen, we can now use one baseline example for it. And to summarize this is what we've got, kind of got pushed off to the side. I'll like move this all over if I can. Really don't want to move today. Okay, that's fine. So to summarize all of this and like make this as a more easy table, we've got all of these different values, whether our delta H is going to be positive or negative, how that's going to be interacting with our delta S, whether it is also favorable or unfavorable for our reactions. And we can see which reactions are actually going to be spontaneous and product favored at most all temperatures or only within certain temperatures. Because if we change our temperature, we might be adding a lot more energy into a system where a reaction is more likely to occur. And if we cool it off, then we might start getting reactions that are less favorable overall. So we've got all of these different situations and scenarios. There's a really nice graphic version your textbook also has of this that I like, where overall we have our 1 delta G over here. Everything that falls into this area is going to be a spontaneous reaction, and everything that falls up here is non-spontaneous. So that's going to be our negatives and our positives. But because we can change the temperature, which is going to really impact our entropy, we can possibly have something that at like higher temperatures might be spontaneous, but as that temperature starts going up, this is the line for temperature. So as we are increasing that temperature, it might be changing whether or not that reaction is actually spontaneous or not at that level. So I just like visuals with that. Yeah. So we might start off with something where at room temperature, a spontaneous reaction won't occur, but as we get hotter and hotter and hotter and hotter, it starts becoming more spontaneous. How do you feel about this?
The classes.
Hmm?
This class 1, class 2, class 3, class 4, what does that mean?
Those classes are kind of just referring to
Oh, I
this
see.
chart. I just need to move them back together and it was just being really stubborn moving. So it's literally just responding to each of those different scenarios because those two things went together. Cool. That is all I've got for us today. Um, we are going to have one of our social justice presentations on processed foods and how good or bad or terrible this might actually be for us. So if one of you can send me your presentation, that'd be awesome. Cool. Is anybody doing the hot chocolate run this weekend? There's a thing in the Daily Digest about some hot chocolate run in Northampton. So me, Sarah, Jenny, and possibly the Ava the dog might all be running around. We'll see how good she is. It's only like 5K. She hasn't done big crowds of running yet, so I'm a little anxious about bringing her there, but kind of really want to try it. All right, if you two want to come on up. In 2 seconds. Think about it. Think about it. There we go. Cool. Push the buttons for the slides. Otherwise, show is yours.
Hi, everyone. We're doing our presentation on processed foods. Take it away, Martin.
So, unfortunately, there isn't a universally agreed upon system to classify foods by how processed they are. But the NOVA system is by far the most commonly used one, so we'll be going off of it as well. It uses 4 groups. Group 1 are unprocessed or minimally processed foods like an apple. Group 2 are processed culinary ingredients made of food from Group 1. And then processed foods are Group 3, and that's usually made by adding common ingredients you might find in a kitchen to an unprocessed food and then combining them through baking or canning. So like a cake or canned vegetables. They're basically combinations of Group 1 and Group 2 usually. And then ultra processed foods or UPFs are manufactured with substances you'd rarely find in a kitchen like high fructose corn syrup or protein isolate powder. Whereas processed foods are usually made by combining Group 1 and Group 2. Ultra processed food is kind of its own beast and a lot of the time includes little to no Group 1 food. The main characteristics of UPFs is that they are heavily processed and have a variety of additives, particularly those made industrially. While certain unhealthy foods are not considered UPFs and certain UPFs are considered healthy, a majority of UPFs are unhealthy. Consumption of these have been linked to increased risk of obesity, cardiovascular disease, type 2 diabetes, mental disorders like depression, and then cancer, hypertension, and just generally count towards a lot of mortalities. Junk foods, processed meats, and drinks with added sugar are the biggest sources of these issues. They're carefully and scientifically designed to be hyper palatable, which means what it sounds like. They're optimized to be as tempting as possible and get you addicted. Exceedingly common ingredients like saturated fat, sugar, and salt trigger dopamine release and contribute to a very high caloric density, which is like the main cause of obesity. Snack foods are also processed to have an unusually soft structure in a way that makes them much easier to digest, to the point that they bypass the body's need to break down food, and the extreme speed at which your body absorbs their fat and sugar combined with the high caloric density of those ingredients usually leads to you overeating before your body can even send a signal to your brain that you're full.
And this is just kind of talking about the cool, well, it's kind of sad, but kind of cool chemistry behind why these are potentially dangerous. And I'll take a look at normal food processing and then also some like really high ultra processed foods. So one example is, oh, this is supposed to be raising concern, but it's blocked by meat. My bad. But So meat in higher temperatures, such as pan frying or even cooking it over like an open flame, results in the formation of some carcinogenic chemicals known as heterocyclic amines and then polycyclic aromatic hydrocarbons. And so how these two they kind of go hand in hand. So when amino acids and some sugars and compounds found in muscle, so also found in meat, like creatine, react at a high temperature, they lead to the creation of those HCAs. And then as the meat is grilled over open flame in particular, fat and juices from that meat, they go under the flame, create smoke, and then those create those polycyclic aromatic hydrocarbons, which then stick to the meat's surface. And fun fact, it's also found in the car exhaust and cigarette smoke and things like that. But when you ingest the meat that's been cooked, it goes through a series of enzyme activation called bioactivation, which then can cause damage to the DNA. And then in some animal model research, that's been revealed to lead to risks of cancer in rat models specifically. You get into the next one. Thanks, Martin. Um, as well as that, acrylamide is a chemical that's mostly used to create polymers and copolymers that are used in industrial processes. A lot of things like making plastic, making paper, caulking, even like drinking water and wastewater. It's also in certain foods like potatoes, but it's in very, very minimal dosages. But it's kind of cool that potatoes, when they're heated, they have the amino acid asparagine, which react with reducing sugars, and then that produces acrylamide, which is also in cigarette smoke. So it's kind of interesting how it's in like a organic natural food like potatoes, but also in cigarette smoke. But the main culprits of foods that have high doses of acrylamide are French fries, potato chips, crackers, bread, cookies, breakfast cereal, prune juice even. But they have higher sources than normal of that. But it's also linked to cancer in rodent models as well. It's transformed by the body into glycilamide, which is a substance that damages and mutates DNA, similar to the uh, heterocyclic amines, things like that. You can get the next one. Another one is absorbic acid, which is just a fancy way of saying vitamin C. And preservatives like sodium benzoate, they react particularly in soft drinks. The sodium benzoate is usually put in soft drinks to stop bacteria, yeast, and mold from growing. However, particularly in reactions that involve heat or light, tiny amounts of benzene are created, and that is like a known carcinogen, like very bad. In the science community, just a known carcinogen. But and then you get the next one. Last one is nitrites, which I love cured meats. This is like very sad. I'm still going to eat it anyway. But in cured meats, they enhance savory flavor and the delicious pink hue of cured meats. They're mainly added to prevent harmful germs from growing and to inhibit the oxidation of proteins and lipids and fats in meat products. And then because sodium nitrate in particular is inexpensive, that's why it's used. But it is associated with the synthesis of nitrosamines, which are carcinogenic. So that's an interesting relationship there. And then you can hit the next one. And then another thing is like, when you're eating these foods, it exposes you to these chemicals that can potentially harm you. But another thing to think about is similar to the radium girls, it's like workers in this industry are also exposed to a lot of the, offsets that come from food processing. So sanitizing agents like disinfectants and combustion byproducts like CO2, nitrogen oxide, then food allergens that become airborne. So, it happens a lot with powdered eggs. If you're allergic to that, it can create some respiratory issues. And then cleaning chemicals, lubricants, and anti-corrosion agents, they can lead to skin irritation, and then similar to the cleaning chemicals like respiratory issues and things like that. And then going back to a real world example, but studies have shown that workplace exposure to the acrylamide that was mentioned previously, it, when you inhale it, it causes neurological damage. And then, with the evidence we have that it suggests carcinogenic behavior, it's kind of like, well, I'm sure we can also form a relationship there to having cancerous risks and things like that.
So UPFs come with a lot of downsides, but you can't really just cut them out. For one, they don't have to be unhealthy. In fact, the NOVA definitions for food groups doesn't make any direct mentions to the nutritional value of the food in each group. And it wasn't originally intended to be used to sort food by how healthy it is, only by how processed it is. Whole grain bread, baked beans, and most non-plain yogurts are technically ultra processed, but they're still pretty good for you. And also a huge amount of the US food supply is ultra processed. So having a sudden shift away from UPFs as a whole is just unfeasible. And then another thing complicating the idea of avoiding all ultra processed foods is their convenience. They're typically cheap, very calorie dense, and ready to eat. And 100 calories of unprocessed foods is on average about 3 times as expensive as 100 calories of ultra processed foods. So that brings me to maybe the biggest roadblock in cutting back on UPFs, which is that not all people eat an unhealthy amount of them because of their addictive nature. Some people's diets include a lot of UPFs because they don't have much choice. They're consumed in disproportionately high amounts in food deserts, low-income households, and especially among communities of color for some previously stated reasons that healthier options just can't compete with their affordability, availability, shelf life, or the low to non-existent time needed to prepare ultra-processed food. Because of this, stricter regulations or outright bans can't be the solution on their own. The alternatives would also need to be made viable for people who depend on UPFs. And we have questions. Yeah, so some of our questions were like, how would you approach the problem of unhealthy UPFs without restricting some people's access to food? What connections can we make between worker safety now versus then? And do you think a new system for food's nutritional value and level of processing should be created? And how would you structure it if so?
I would love to talk about the first one. It's like, how do we address like, especially right now where there's a lot of like major food drives and things like that for people who are in need, that we just went through like SNAP benefits being lost for our folks for a while. And so everybody was donating a lot of canned foods or things that are easily microwavable, which that also means that like the people who are most at risk of like hunger and starvation are also most exposed to it. Like, does anybody have any thoughts on?
Another thing is that sweeping legislation that is meant to hold back ultra processed foods will not only stop unhealthy foods, because like we said, since they are usually correlated, they don't always go hand in hand. So there's still going to be a lot of unhealthy food that isn't ultra processed that wouldn't be affected, and there's a lot of very healthy food that would be affected.
I mean, based on your presentation, it seems like a lot of the problem is like, it's kind of like designed to be addictive, is what I'm saying. Like I'm kind of hearing two different problems, like that's like designed to be like ultra consumerist and food's just like designed to be like convenient and accessible. Like, I don't know, like to your point of like how do we make like, I guess, less processed, or I guess to healthier food, it's not really the word I want. I guess like less processed food, more accessible to like like uh communities with less access, or like food deserts, for example. Like I'm honestly thinking about my time over somewhere on this campus. Like this place is to be like basically a food desert. Getting food here is really fucking hard. Um uh but like we have things like more decentralized resources like a farm, which I think really help. So having resources like that that aren't like dependent on like the global supply chain to actually supply like fresh food. Like I can like often like we'll have like vegetables in the hamster and such, and I think that those resources are really good. They obviously don't like fully supplement like someone's food need. I don't know. I think things like that are really good, just like decentralization in general. But I don't think that addresses the problem of actual like like the other problem of the of other
Hyperpalatable.
ultra processed food.
Yeah.
Yeah, I think that's super well said too about like farming and how like useful that is. Cause it's like, I think, well, I mean, UPS are so popular because it's just like, I guess they're cheaper to make ultimately. So like, it's gonna drive like some corporate, for lack of a better word, like corporate greed. But it's also like, I mean, I put that map of, it was like a map of New York in there because I know that Harlem especially, majority of people of color neighborhood, and like there are no grocery stores over there. People cannot get food. They can just rely on like the bodega, which doesn't have fresh produce or anything like that. So I think like implementing farm education and like the usage of that, especially within people of color, is like that's a great initiative. I'm sure that there are organizations doing that, but it's a really great point that you brought up. You all can stop.
Okay. Actually, wait, I watched a documentary about like getting gardens started in like Black communities earlier in the year. I think a huge part of it is like giving people these resources is like one part of the problem. Being able to give them something that they can continuously use over a long period of time, like a community garden or like some space that is not just going to go away, is really important. And also like decreases the level of dependence that we have on the, centralized ultra processed foods.
I mean, the other thing to keep in mind is that when you're in that situation, you're not just like short of money, you're also short of time.
Yeah,
And things like that take like a fuck ton of not just like monetary resources to actually buy the land and like have like the space to do it, but also like the knowledge to do it is like
Yeah.
I don't know, like
well,
difficult.
that's part of it too, is like community garden. There's going to be more people there than just yourself, ideally, that are going to be contributing. And the other thing too, I think it'd be interesting to find a way to make it profitable for farmers. Like if you think of like local farmer markets coming to town, it'd be interesting to find a way if they can make it profitable for them to be giving resources to lower access,
It's so
Yeah.
multifaceted and complicated.
Yeah.
I mean, also with like the time thing, it's like thinking about like lower income communities. It's like if you are lower income, you need to work more to afford to live.
Yeah.
So it's like time is a big thing. I mean, even with like farmers markets, like I was, I don't know, just like thinking about how like farmers come into town, they're gonna sell their goods. It's like, when does that normally happen? During like weekdays, work time? I don't know. Just like maybe an evening farmers market. I don't know.
Yeah.
Now I'm excited because I'm just like,
Yeah,
there's so many things we can do, but
I think that. Oh no, go ahead.
Oh, I actually, throughout the summers, I worked at a local farmers market. And it would go on, at least the one in Clintonville would go on every Saturday. And it'd be like all Saturday long. But then for specific areas in Ohio or different cities, they would have some like in the evening, or they'd have one of the weekdays, like after work, basically.
that's super cool.
Yeah.
I obviously can only draw from my like personal experience, but I was in Berlin very briefly, and they had farmers markets as like a almost like a as like a replacement for grocery stores almost. Like it was very much not like oh yeah, this is like upper middle class like getting their like vegetables. Like no, this is like working class, like this is like the cheapest available option. So I guess I guess what I'm saying is that like I think it definitely is like a viable option. It's just like the structure and community needs to be there, which is like hard to fix.
I also don't know anybody at a farmer's market who would give somebody free food.
Right.
Like I've given people free food.
Yeah.
Yeah.
Need food to live.
Yeah.
It's incredibly important.
I mean, back to like legislation stuff, like I know the FDA does stuff with like this is the amount of like this chemical or this ingredient that we see these like carcinogenic effects on. And so the allowed amount is like 100 times less. Like, could that be a way to like sort of target specific ingredients or specific amounts and not just ultra processed?
So I think that's a really, really cool point.
It's a good idea to target not just ultra processed foods or any one group in the Nova system in general, since even though it's ended up being used this way, it wasn't for nutritional values. But it's a fine idea in theory until Coke says that putting less sugar will hurt their profit margins, and they lobby to stop that.
Oh, like the new Coke when that flavor came out and everyone got really mad 'cause it tasted different.
Sort of, but also there's just they make so much money because it's so cheap and easy to make ultra processed foods, and they sell them and they make them addictive and stuff, that they kind of have enough money to just stop a lot of legislation that would get in their way.
Yeah, it's likely.
Yeah, I saw it in some articles.
I think one of the biggest problems is the amount of waste we have in this country. It's not that there's not enough healthy food to go around for everybody. There's more than enough. There's an abundance of food, but so much food gets thrown away, and that's also a symptom of capitalism. But I was just gonna say, if anybody in this classroom is facing food insecurity, local resource, Amherst Survival Center has fresh food from local farms, totally free. You don't need to provide very much information about yourself. And it's one of the rare places where you can get like farm fresh food, in that kind of situation. Like most food pantries will have, mostly canned goods or boxed goods and things like that. But so if you need healthy options, shout out Amherst Survival Center, PDPA, go straight there.
Also on campus, there's the student resource center, but that's more like.
Yeah, I'd be in there.
Your fidget things, vegetables.
There's like an app where you can like.
Oh, is it the,
Yeah.
no, it's not
Oh,
got
Too Good to Go.
Too Good to Go.
Yeah, it's like-
Yeah, I use that all the time.
Yeah, but
Yeah.
to me, it's like, if we're making that into a like resource, why couldn't that also like be free? You know what I mean?
Exactly. I
Yeah.
mean, that point of bringing up the waste time, I didn't even think about putting that in this presentation, to be honest, but it's like that's an excellent point. I mean, if you go outside Aldi, like even Aldi here, it's like there's like literally just like produce like in the dumpster. I mean, even in New York, sometimes I know like they have the people that like stand by the dumpster to watch you to make sure you don't wet them, which is so like 1984, like Big Brother, like what? That's so strange, but I don't know. It's shameful, but yeah. But thanks for pointing out that resource.
Anything else?
I think the preservation techniques also think a lot of the things you mentioned as like carcinogenic or harmful chemicals are used as preservatives.
For canning.
Yeah.
What one in particular? Do you remember?
Oh, the one that really struck out to me is the one that was in soda.
Yeah, is it the absorbic acid or
Yeah, the bentonate.
Yeah. So that's like only under like intense exposure to like heat or light, which sometimes can happen in the like transportation process. But I don't know if that interferes with canning. I would hope not. I don't think it would.
Yeah, but I think I don't know. I think there's a lot of people were preserving food for a really long time without using chemicals.
Yeah.
So, but like that, there's also becomes a time when you think of those methods take a lot of time or are more expensive.
When I saw that, it's like, so if you were drinking a soda outside in the heat, would that mean that?
I actually looked
Like-
that up and Google didn't
Yeah.
tell me anything. Even
Oh,
my,
so
my,
they don't
my,
want us to
my
know.
G, my
They don't want
my
us to
Google
know.
Scholar PubMed, they didn't. I like looked
Yeah.
up I like looked up like 80 variations. I was like, soda cooking, heat, frying pan, soda warm. Like it is, yeah.
Yeah, 'cause that's
Yeah.
the first thought I had when I read that. I was like, everyone drinks soda when outside in the summer, like at a barbecue or
Yeah.
it's sitting out for hours.
Well, it also depends if the soda contains like I forgot what it was, but the absorbic acid and the sodium benzoate together.
Okay.
Sometimes I think from the research that was, because this is from like 2023, or no, not the I didn't put it here, but it's like I think that they don't use those anymore, I'm pretty sure, but it was in the past. Yeah,
Maybe they don't use them together.
I don't believe so, because it's like, because benzene's like bad, like very, very bad. And so yeah,
Is there a potential issue with like vitamin C in our body already?
I don't believe so, but also it's not within my scope of practice to say whether or not.
I really want to go take a tour of the Coca-Cola has a giant factory for canning in Northampton. I really want to go, but they are very secretive about letting you actually see what processes.
I'm sure. Their trade.
But their wastewater is like pH 9 or 10, like it's really, really high because they expend so much other chemicals making, like soda is pH 2 or something.
He doesn't say how second so basic.
Hmm?
I'm just shocked that's so basic.
Yeah.
It's, I wanna know what's in it, but they won't. They won't let us know.
Okay, thank
All right,
you.
cool, yeah. Cool, I think we have one more presentation class, maybe. Maybe. Yes, we have one more presentation next class. We've got our final lecture, where we're gonna talk more about reaction kinetics and stuff like that. It'll be thematically math, but I need you to just understand like conceptually what's happening. You like for most, like you're not gonna be quizzed on that during like the final exam. At least none of the math of it. So, yeah, it'll be fun. It's cool stuff. Thanks. Let me know if you're coming tomorrow or if I can help you coordinate anything. Because I imagine you want to go downstairs and check BOD soon.
Like, yeah.
Yeah,
Like
what-
now.
like now. Great,
If
cool.
you have
I got time. It's the game plan. Cool.